Hi friends, today I am giving a lecture on instruction cycle. Instruction cycle is one of the most important concept in computer organization. An instruction cycle mainly contains three subcycles. First one is fetch cycle, second one is decode cycle, third one is execute cycle. Okay, in fetch cycle, fetch phase reads the instruction from the memory and send it to the CPU. Okay, we can simply say that the fetch cycle reads the instruction from the memory and send it to the CPU. Next, second one, decode cycle. So in decode cycle, we have to decode the opcode by using 3x8 decoder. Okay, so then we have to determine what is the operation to be performed. Okay, third point, execute. In the execution cycle, we have to execute the indicated operation. Okay, so this diagram shows the basic instruction cycle. So in that one, first start, second one, so fetch the instruction from the memory and send it to the CPU. So this can be done in fetch cycle. In decode cycle, so we have to decode the opcode in the instruction by using the 3x8 decoder, because the opcode contains 3 bits as input. It produces 2 power 3, 8 outputs. So we have to use 3x8 decoder. So then we are getting 8 outputs. Each and every output specifies a particular operation. Okay. Next one, in execution cycle, we have to execute the instruction by specifying the indicated operation. So what is the operation that is specified in the instruction? So that operation is executed in execution cycle. Once the instruction is successfully executed, again it goes to the fetch phase. Now the fetch phase reads the next instruction from the memory and send it to the CPU. So this can be done repeatedly until all the instructions in the program are completed. Okay, so this diagram is the basic instruction cycle. In this one, there are 3 subcycles are there. First one is a fetch cycle, second one is a decode cycle, and third one is execute cycle. Okay, now we go for each and every subcycles. Okay, initially the program counter PC is loaded with the address of the first instruction in the program. Okay, suppose we can take a program. In that program, the first instruction address is 1000. Then PC contains the address 1000. Okay. To providing the timing signal T0, initially the sequence counter SC is cleared to 0. After each clock pulse, sequence counter is incremented by 1 to provide a sequence of timing signals T0, T1, T2, T3, T4, etc. Okay. Next, fetch cycle. So this is the first subcycle or first phase in the instruction cycle. Okay. The register transfer statements for the fetch cycle are: at T0, the content of PC are transferred to address register AR. Okay. What is the content of PC? PC contains the address of the first instruction in the program. Okay, that address is transferred to the address register AR. Okay, at timing signal T0. Okay, next at timing signal T1, whatever the address that is transferred to the address register, okay, that address is read from the memory. Okay, whatever the instruction is there in that address, so that instruction is transferred to the instruction register IR. At that time, PC value is incremented by 1. So now PC points to the address of the next instruction in the program. Okay, these two operations can be done at timing signal T1. Okay, so these T0 and T1 operation timing signals can be done in fetch cycle. Okay, so now how T0 operation can be done? Okay, so here there are three registers are there. First one is program counter PC, second one is address register AR, third one is instruction register IR. Okay, so this is memory unit. So all these four components are connected by using a common bus. Okay, initially PC contains the address of the first instruction in the program. Okay, that address is placed onto the common bus by enabling the input Y2. Y2 is nothing but 2 by setting S2, S1, S0 value is 0, 1, 0. Here 2 can be written as 0, 1, 0. So 0, 1, 0. What is the output it is selected? That is Y2 is selected. Okay. So that means the content of PC, that is nothing but address of the first instruction in the program. So that address is placed onto the common bus by setting the inputs S2, S1, S0 to 0, 1, 0. 0, 1, 0 is nothing but 2. So then the output Y2 is activated. Okay. Now the content of the common bus. The content of the common bus is address of the first instruction of the program. Okay. So this address, the content of the common bus is nothing but address of the first instruction is transferred to the address register AR by enabling the load input. So up to this point, so this operation can be done. Okay. So what is the first operation? The content of PC is placed onto the common bus by setting the inputs S2, S1, S0 as 0, 1, 0. 0, 1, 0 is nothing but 2. 2 is nothing but Y2 output is activated. Okay. Whenever the output Y2 is activated, the content of PC is placed onto the common bus. Okay. Now, in the second step, the content of the common bus is transferred to the address register AR by enabling the load input. Now, the address register AR contains the address of the first instruction in the program. Okay. So, this can be done in T0 operation, in T0 timing signal. Okay. Next. In T1 timing signal, what is the operation can be done? Okay. So, that whatever the address that is transferred to the address register, okay, that address is read from the memory by enabling the input. So that is by enabling the input Y7. Y7 is nothing but 7. 7 is nothing but 1, 1, 1. 1, 1, 1. By setting S2, S1, S0 as 1, S2, S1, S0. S2, S1, S0 as 1, 1, 1. 1, 1, 1. So Y7 output is activated. Okay. So Y7 output is activated means, okay, whatever the address is transferred by the PC, that address is stored in address register AR. Okay. Now this address is read from the memory by setting S2, S1, S0 as 1, 1, 1. Whenever S2, S1, S0 as 1, 1, 1, so the output Y7 is produced. So then the content of AR is read from the memory. Okay. So then after reading, then it places the address onto the common bus by enabling the input S2, S1, S0. Next one. The content of common bus can be transferred to the instruction register IR by enabling the load input. Okay. So that means once the address can be read from the memory by setting S2, S1, S0 as 1, 1, 1, then the decoder output Y7 is activated. So now the content of the common bus is transferred to the instruction register IR by activating the load input LD. Okay. So up to this point, this is completed. Next, after that, the content of PC is incremented by 1. So the content of PC is nothing but PC is always points to the address of the next instruction. Okay, by enabling the input Y2. So by enabling the input Y2 is nothing but by setting S2, S1, S0 as now PC is incremented by enabling the input INR. Okay. So after that PC is incremented by 1. So PC is incremented by 1 by enabling the input INR. Okay. So after enabling the input INR, the PC value is incremented by 1. Now the PC always points to the address of the next instruction to be executed in the program. Okay. So these three operations can be done in T1. Okay. So these two operations can be done in T0. Okay. Once again I am telling, okay, in T0, okay, initially the content of PC, that is nothing but address of the first instruction in the program, is placed onto the common bus by setting S2, S1, S0 as 2. 2 is nothing but 0, 1, 0. Whenever S2, S1, S0 as 0, 1, 0, according to that the output Y2 is produced. Okay. So at that time the content of PC is placed onto the common bus. Okay. Next, in the second step, the content of common bus is transferred to the address register AR by enabling the load input. Okay, so these two operations can be done at T0 timing signal. Okay, next one. In T1 timing signal, okay, the content of whatever the address that is transferred into the AR, so that address is read from the memory by setting the S2, S1, S0 as 7. That means 1, 1, 1. So whenever S2, S1, S0 as 1, 1, 1, that is 7. So Y7 output is activated. So now that address is placed onto the common bus after reading that address from the memory. Now the content of the common bus is transferred to the instruction register IR by enabling the load input. Okay, so after that the PC value is incremented by 1 by enabling the INR input. Okay, so these three operations can be done in T1 timing signal. Okay, so these two operations are done in fetch cycle, in timing signal T0, in timing signal T1. Next we go for decode phase. Okay, so this diagram shows the implementation of register transfer instruction for fetch cycle. Okay, so next phase is decode cycle or decode phase. So this decode phase that can be done at timing signal T2. The register transfer statements for decode phase is: first, the currently executed instruction is transferred to the instruction register IR from the address register AR. So now the currently executed instruction is stored in the IR register in the 16-bit format. Okay, so this is IR register. So this is 0 to 15, that is in the 16-bit format. The currently executed instruction is stored in the instruction register IR. So in this one, first 0 to 11 is nothing but address. This address is transferred to the address register AR. Next one, 12, 13, 14. So these bits represents the opcode. Opcode is nothing but what is the operation to be performed. Okay, these three bits in the opcode are decoded by using 3/8 decoder. So it can take 3 bits as input and produces 8 bits as output. So 3 bits are 12, 13, 14 are 3 bits. These 3 bits can be taken as input by the 3/8 decoder. It produces 8 outputs, that is D0 to D7. Okay. Next one, the 15th bit of IR register is transferred to the mode bit, direct or indirect mode bit, capital I. Okay, so these three operations can be done at T2 timing signal. Okay, bits 12 to 14 of instruction register IR are decoded using 3/8 decoder. It produces 8 outputs, D0 to D7. Okay. Next, second step, bits 0 to 11. Bits 0 to 11 of IR register is transferred to the address register AR. Next, third operation, bit 15 of IR register is loaded into the direct or indirect mode bit capital I. Okay, these three operations can be done in decode phase at timing signal T2. Okay, so now determine the type of instruction. Okay, there are three types of instructions are there. First one is memory reference instruction. Second one is register reference instruction. Third one is IO reference instruction. Okay, so now observing the decoded output D7 bit. So if D7 bit is equal to 0, then that instructions can be treated as memory reference instruction. D7 value is equal to 0. We can say that it is a memory reference instruction. D7 value is equal to 1. So it is either register reference instruction or a IO reference instruction. Okay. So here the decoded outputs are D0 to D7. Now observing the D7 bit. By observing the D7 bit, we have to determine the type of instruction. If D7 bit is equal to 0, then it is a memory reference instruction. If D7 bit is equal to 1, it is either register reference instruction or a IO reference instruction. Okay. If D7 value is equal to 0, that means D7 bit value is equal to 0. It is a memory reference instruction. If D7 bit value is equal to 1, it is either a register reference instruction or IO reference instruction. Okay. Now this table shows which type of instruction is to be executed. If D7 value is equal to 0 and I bit, next we go for fourth phase of the compiler is the intermediate code generation. Intermediate code generation is the fourth phase of the compiler. After the syntax and semantic analysis, some compilers may produce or generate an explicit intermediate code generation for the given source program. Okay, that means for a given source program, after the syntax and semantic analysis, some compilers may produce an explicit intermediate representation of the given source program. The intermediate code representation of the source program has two important properties. First one is it is very easy to understand. Second one is easy to translate into target program. Okay, we can easily translate the intermediate representation of the source program into target program. The intermediate representation of the source program is very easy to understand. Next one is the intermediate code representation can be represented in so many forms. So one of the most important form is 3 address code. What is 3 address code? 3 address code is a sequence of instructions. Each and every instruction can have at most 3 operands. At most 3 operands is nothing but it may contain 1 operand, it may contain 2 operands, it may contain 3 operands. Okay, each and every instruction may contain at most 3 operands. Suppose we can take a given statement, position is equal to initial plus rate into 60. How we are converting this given statement into 3 address code. So here 3 address code means each and every instruction or statement contains at most 3 operands. Okay. So for example, this is the statement. So this statement can be converted into 3 address code. So first one is temp1 is equal to int to real of 60. Okay. So in this one, highest priority given to into operator. So for that one, first we are converting the integer 60 into real by using int to real operator. So that is temp1 is equal to int to real of 60. Okay. Second one is after converting this integer 60 into real, it can be multiplied with the identifier rate. Identifier rate can be treated as ID3. ID3 into whatever the result we are getting, that is temp1. So ID3 into temp1, that can be assigned to temp2. So now we are getting this result. First, temp1 is equal to int to real of 60. That is the first statement. Second statement is whatever the result we are getting, that result is multiplied with identifier ID3. Whatever the result we are getting, that result can be assigned to temp2. Okay. Next, whatever the result we are getting after this temp2, that can be added to the identifier ID2. So this is this result is ID2 temp2. Temp2 can be added with ID2. Here ID2 is nothing but initial. Okay, this result can be assigned to the variable temp3. Okay, now whatever the result we are getting, this is the total result is temp3. Temp3 can be assigned to the position. Here position is nothing but ID1. So here temp3 can be assigned to the ID1. So each and every instruction can have at most 3 operands. So here 2 operands are there. Here 3 operands are there. Here 3 operands are there. Here 2 operands are there. Okay. So these instructions fix the order in which operations are to be done. Here we have to fix the order in which operation are to be done. Next one is fifth phase of the compiler is code optimization. Here mission independent code optimization. Here we have to use mission independent code optimization. Here mission independent code optimization attempts to improve the intermediate code representation to get the better target code. Okay, we can get the better target code by improving the intermediate representation of the source program. That can be done by mission independent code optimization. In some compilers, the code optimization followed by intermediate representation to get the better target code. Next, the above optimized code. Next, the above intermediate code representation. Next, the above intermediate code representation can be optimized in these 2 statements. In the intermediate code representation, the first instruction is temp1 is equal to int to real of 60. Second instruction is temp2 is equal to id3 into temp1. Okay, here the conversion of integer 60 into int to real, that is 60.0, can be done all at once at compile time. so that that instruction can be eliminated. Okay. Next one is final result temp3 can be assigned to identifier ID1. So this instruction is also eliminated. So whatever the result we are getting, that result can be directly assigned to ID1. Okay. The above intermediate code representation can be optimized into these two instructions. So first one is temp1 is equal to ID3 into 60. Okay. So in the intermediate code representation, the first instruction temp1 is equal to into real of 60, that can be eliminated. Next one is, so temp1 is equal to ID3 into 60. Okay, this is the second instruction in the intermediate code representation. By eliminating the first instruction, this is the second one. Temp1 is equal to ID3 into 60. Now, whatever the result we are getting, that is temp1. Temp1 means ID3 into 60. This means is ID3 into 60. Whatever the result we are getting, that result is temp1. This temp1 can be added to the identifier ID2. Whatever the result we are getting, that result can be assigned to ID1. Okay. So I will show temp1 is equal to into real of 60. Temp2 is equal to ID3 into temp1. ID3 into temp1. Next, temp3 is equal to ID2 plus temp2. Next one, ID1 is equal to temp3. So this is the intermediate code representation. So this statement can be eliminated because at the compile time, all the instructions at once that are converted into real, so that this instruction can be eliminated. Next, this is direct instruction. So now temp1 is already, this instruction is already eliminated, so it can be written as temp1. Temp1 is equal to ID3 into temp1. Temp1 result is directly 60.0. So therefore, this instruction can be written as temp1 is equal to ID3 into 60.0. Next one, this is temp1. Now we can take temp2. Temp2 is equal to ID2 plus here whatever the result we are getting, that is temp1. So that can be directly assigned, and this instruction is also eliminated because whatever the result we are getting at instruction 1, that can be directly assigned to ID1. So these 4 instructions are intermediate code representation. This intermediate code representation can be optimized into these 2 instructions by eliminating this one and by eliminating this one. Only 2 instructions are optimized code instructions for the given statement. Position is equal to initial plus rate into 60. Okay. Next, go for last phase, that is the 6th phase of the compiler, that is code generation. Code generation is the final phase of the compiler. In the code generation phase, so whatever the intermediate code representation of the instructions that are converted into some optimized form. Okay, so whatever the result we are getting at the fifth phase of the compiler. So that is the input for the code generation phase. So here the code generation phase converts the given intermediate optimized code into the target code or mission instructions or assembly code instructions. Okay, the code generation phase converts the intermediate code instructions or optimized code instructions, each instruction translated into a sequence of mission instructions or assembly code instructions. Okay, whatever the optimized code we are getting through code optimization, that can be converted into a sequence of mission code instructions or assembly code instructions. Okay, the memory required for each of the variables that can be assigned by the program. So the program can assign the memory for each and every variables that are used in the instruction. Okay, next here for the given optimized code, so what is the code generation phase? Code generation phase generates. The code generation phase generates the target code for the given optimized code by using two registers, that is R1 and R2 registers. Okay, so in this one, the source operand, that is the source operand is this one. The source the first register, the first operand specifies the source. The second operand represents the destination. Okay, this is the source and this is the destination. This is the source, this is the destination. Okay, so in this one, F denotes the each and every instruction deals with floating point representation. Okay, first one is move F ID3 R2. Okay, whatever the ID3, the content of ID3 can be moved to R2. So now R2 contains, that is ID3. ID3 is rate, identifier rate. Next, multiply has 60.0 with R2. Okay, so now R2 contains, so rate is multiplied with 60.0. So now initially the register R2 contains only identifier ID3. Okay, now after the second instruction is completed, so hash 60.0, that is the converted real number 60.0 is multiplied with the identifier ID3, that is rate. Now the result is, so rate into 60. Okay, next one, move F ID2 comma R1. So now R1 contains ID2. ID2 is initial. ID2 is initial. Next one, add F R2 comma R1. So now R1 contains initial plus R2. Okay, initial plus R2. Initial is identifier ID2 plus R2 means rate into 60. So now move F R1 to ID1. So now ID1 is equal to, so initial plus R2. So that means initial plus ID3, that is the rate into 60.0. So the final result is there at ID1. So this is the ID1 is equal to ID2 plus temp1. So ID2 is initial, temp1 is nothing but rate into 60. Here the first one deals with the source operand, the second one deals with the destination operand. Here F F means each and every instruction. F contains that deals with the floating point instructions. In the above optimized, in the above in the above target code, each and every instruction contains F. F deals with instructions or deals with floating point numbers. Next, hash 60.0 represents the constant. If the symbol hash before 60.0, then it can be treated as constant. Okay. So next one is symbol table management. So symbol table is a data structure that is used for storing the identifiers as a record. So here each and every record can be allocated for identifiers. Okay. Next one is, so each and every identifier has some fields. In that fields we have to store the attributes of the identifier. Okay. So a symbol table is a data structure. In that data structure, a record is there for each and every identifier, and also some fields for storing the attributes of the identifier. Okay. This data structure allows to store the identifiers and to find any identifier so quickly. So that means to access the identifier as early as possible. For that purpose, we have to use this data structure. Okay. And also we have to store the identifiers and its attributes in that record. For that purpose also we have to use this data structure. So that means